Hello there. Today we're going to look at xLSTM, Extended Long Short-Term Memory by Maximilian Beck, Corbinian, Pöppel, and a team around them. Especially the corresponding author here is Sepp Hochreiter, who you may remember was the original, or among the original inventors of LSTMs, Long Short-Term Memory Neural Network, the most popular type of recurrent neural network there was, invented in the 90s, obviously, where all the good things were invented. And this paper is a new take on an LSTM with all the learnings that we now have from the LLM world, like from the world of transformers and so on. So the central question here is how far can we push LSTM type architectures or recurrent architectures in general, and how much can they compete with transformer-based models or attention-based models when it comes to specifically language modeling. So obviously, I don't know, but if let's say there is something to this, right? Then that would be a huzzah back for the LSTM authors. So there's also maybe a bit of personal interest right here, but I do think it's a cool work in a cool direction. And notably, it ties into a bigger picture around, does it even matter what architecture we have? Do only parameters matter? What's really important in these kinds of things? And we can get into all of that a bit later. But first, note the beauty here. The paper starts with in the 1990s. You're about to read history when a paper starts with the words in the 1990s. Yeah, in the 1990s, I can't really remember much of that time, but some people can. And this paper says the constant error carousel and gating were introduced as the central ideas of the long short-term memory. Since then, LSTMs have stood the test of time, contributed to numerous deep learning success stories. In particular, they constituted the first large language models. Already, we're out of the gates with extraordinary claims. There is something to be said about LSTMs. They certainly had their impact. They had their impact in numerous domains, right? They were widespread. Their properties make them really good sequence processors, even sequences that transformers struggle with, like time series and, like heart rate data and whatnot, audio data. All of this stuff, LSTMs are applied. They don't use humongous amount of resources and so on. And yes, they were also used for language modeling. Notably, a lot of the machine translation architectures and so on were powered by LSTMs. But I don't know, the 1990s crew must kind of formulate everything that's happening today as, oh, this was already done, right? So now the hype is around large language models, by which we mean specifically language models that take, they go really like big in parameters, really achieve their width and achieve their performance by scaling, right? And then pumping as much data as possible into them. And yes, you may say that some of the language models back then and some of the translation models were kind of that, but always being like, oh, we did that. We already did that back then. We did transformers back then. We did GANs back then. I don't want to get into a fight here, okay? No opinions on those things. I'm just saying, whether it's true or not, the constant, not just referral to, hey, that was great back in the day, but on top of that being like, all of this stuff today, we actually did that already back in the day. Yeah, sorry, rant over. I do have a bit of an issue with the first large language model. I would strongly argue that the first large language models were very probably the n-gram models that in particular Google built on really large scales. Like the number, if you count these as parameters, the number of parameters of these were like through the roof. And therefore, I would seriously consider the LSTMs to not be the first large language models. Like, as long as we're, measuring gonads, I'd be interested in revising that. However, the advent of transformer technology with parallelizable self-attention at its core marked the dawn of a new era, outpacing LSTMs at scale. We now raise a simple question. How far do we get in language modeling when scaling LSTMs to billions of parameters? And that's a valid question. Leveraging the latest techniques from modern LLMs, but mitigating known limitations of LSTMs. And that is a really good question, right? If we have all these learnings from transformers, some of them aren't really particular to transformers. Some of them are just like, you need to normalize your data in between layers in a smart way. Like, yeah, okay, that makes sense, right? You need to use multiple heads if you do sort of single token processing, or if you do processing, it pays off to have multiple heads in an operation. That's fair. We can do that without transformers, right? And a lot of architectures like state space models and so on have actually implemented a lot of these things without transformers. And therefore, you could say, could we apply some of that to LSTMs? Also, could we kind of mitigate the limitations that we know LSTMs have? And if we do that, what happens if we scale them up? Are they going to be as good as transformers? Are they going to be better? Are they going to be worse? Who knows? And the bigger question here is that if you just have like some function, some trainable function, does it really matter how it's built, or is it just the number of parameters that matters? Given that you train it like with enough data and, with learning rates that fit and so on, but does it matter or does it not matter? If it doesn't matter, LSTMs, they do have constant memory usage and therefore, could be a great candidate. They can go for infinitely long sequences. Could be a great candidate. All right, they say we introduce exponential gating with appropriate normalization and stabilization techniques. Secondly, we modify the LSTM memory structure, obtaining two different things. First, sLSTM with a scalar memory, a scalar update, and new memory mixing. Two, mLSTM that is fully parallelizable with a matrix memory and a covariance update rule. Yada, yada, yada. Then they do experiments. The experiments are good. I can already tell you their experiments are good, and then the entire community looks at their experiments and goes like, yeah, and we don't have code yet. So that's the current state we're in. So what they do is they take LSTM here on the left, right, and they modify it in two different ways, like two separate ways of modifying it. The sLSTM is in the most plain sense, it switches out some of the nonlinearities. Some of the nonlinearities right now are sigmoids. It switches them out via exponential function. Then it handles some of the stuff that comes as downsides to using the exponential function because it grows pretty quickly. And then they also have this thing they call new memory mixing. However, that just seems like that's just really new if you look at the really, really old LSTM, but parts of that have kind of already been part of LSTM world for many years, at least the way I understand it. Secondly, they changed the LSTM to the mLSTM. Note, these are two separate things, right? They derive two different cells, recurrent cells, and then they make two different blocks from those, and each block here then serves as a layer in these stacked in a stacked layer sense. So here is depth of the neural network, and they can, for example, switch it with an M layer, then an S layer, then an M layer, an M, an S, like arbitrarily stack these layers on top of one another. So whereas the transformer would only have like a single block that consists of attention and feed forward, This architecture has two different blocks that it chains together in arbitrary fraction, and that's how it propagates signal. So the mLSTM also has the exponential gating. So again, switching out nonlinearities. And then it has this matrix memory. The matrix memory is something we're going to look at. Notably, if you know LSTMs, they have an internal state that they maintain. So they go over the sequence and they try to extract information from each element and put it into an internal state. And then the later sequence elements can kind of read from that internal state, which is really different from the attention mechanism, right? What they do is here they they ask themselves, how can we make this memory have more capacity? The naive way would just to be the increase in dimensionality. However, what they do right here is they have kind of associative memory usage, and we'll get to that. And that comes with this covariance update rule. And that then lends itself to parallel training. Actually, the parallel training is just a result that they kind of drop one connection from, like they drop one hidden to hidden connection, and then it's a parallel, and doesn't seem to hurt, so they can just do it. All right. Then they gate them. Notably, this mLSTM thing is then parallelizable in training like attention is. So we have a lot to get into. First, maybe it's interesting to just see the difference between kind of what, unlike the level that we care about, what attention mechanisms or transformers do, and then what kind of LSTMs do, and why they have fallen out of fashion. So in a transformer, and let's say we're looking at a decoder-only transformer, you have a sequence elements, right? And then I care about forward propagating signal across the sequence. Think of next token prediction or something. So I want to compute signal for this particular token here. And what I do is in each layer of my neural network, I'm able to kind of look at all of the past using attention, right? Dynamically look at all of the past and aggregate information from that. And then at the next layer, again, I'm able to look at all of the past at the same time using the attention mechanism and grab information dynamically, right? Dynamically aggregate information that I need. Now, this has an advantage. Obviously, I get to look at every single piece of information every single time, and therefore that there's almost no better case for, how can you work with sequences. Every element gets to look at every other element in every single step. On the other hand, you may also know that this does have considerable cost, especially since this aggregation here consists of nonlinear functions. Especially in attention, I multiply queries times keys. I do the outer product, and then I do a softmax out of that, and then I multiply that by the values. And this softmax right here is a highly nonlinear operation, and therefore that kind of that denies me the opportunity to do a lot of optimizations. So I have to almost realize this matrix in here, which is really big, or I have to do that sequentially, which costs time. In turn, an LSTM would go over a sequence one by one. So let's say I have a sequence. I want to predict the next token. The LSTM would already have a hidden state somehow. A hidden state. I'm going to draw that here. And that hidden state already has information from all of the past that it has accumulated one by one, moving over the hidden state. So the hidden state already exists, and all I need to do is I need to integrate information from the current element into the hidden state and produce the next hidden state. And from that, I then also produce the output of the current step, either from here or from here. Like from somewhere, I produce the output of the current step. So each step only looks at itself and the last hidden state. So there's information that gets passed from time step to time step, and there is nothing in this that allows me to explicitly look back at the past elements. Now, this is good because it means I just use constant memory, right? I have this hidden state, and it's the same size as this hidden state, and I just need to find a way to update it. So constant memory, and I need to learn a smart way to deal with that memory. On the other hand, not being able to look at the individual sequence elements means that what I encode from this state into the next hidden memory, that's all there will ever be, right? Like no future thing can ever look at this element other than look at the information that's available in the hidden state. So it's almost like you need to learn to extract the exact right things that any future element would want to know of you, and you need to provide it in a compact way, and so that it's addressable, and you need to make sure when you update the memory that you don't override anything that's important that's already there, because you're going to use the same bits to represent that. You see the challenge. That's why originally people developed attention. They said, hey, our RNNs are good, but they would benefit from being able to directly look back like at this element right here. And that's how the attention mechanism was born. And then eventually people said, actually, we don't need this kind of hidden state thing anymore, right? Now, why was this a benefit to not need the hidden state thing anymore? And that's where we need to actually look at how the LSTM is built. And that's what we see down here. So this is the basic form of an LSTM. It has a bunch of formulas, but essentially how you can picture that is there is some sort of a hidden state and there's some sort of an input. And what I want to do is I will output a new hidden state. And I need to somehow decide from this hidden state that comes in, what do I forget? So I need to decide strategically, part of it I will forget. And then of the input here, I strategically decide what part I want to add. Let's say I want to only add the bottom left here, right? And so that gives me something like this. And then I need to find a way to smartly put those two together to make efficient use of the memory. And that's all this stuff here does. A lot of this stuff are called gates, and they call this the constant error carousel. So they have a simplified version of this right here. This here is the hidden state, or part of the hidden state, if you will. They split the hidden state into two different things. One is called C and one is called H. I guess C is for carousel and H is for hidden state, but they're both hidden state. You can think of them as, I don't know, concatenate them, then it's one vector, but you can also just think of the hidden state as being a tuple in an LSTM. The C here is the interesting part in this diagram, or in this formula. You can see that we take the C from the last step and we multiply it by this F thing. Now this F thing is just a number between 0 and 1. By the way, in the original formulation of the LSTM, all of this were just single scalars. So we're just wondering what scalar should we remember. Later, it was extended to vectors. In that case, this would be a piecewise multiplication right here. So F is just a number between 0 and 1, and we call it the forget gate. So if F is 0, it means I forget C. If F is 1, it means I remember. And likewise in the vector formulation, if F is 0 in a particular dimension, it means I forget that dimension. If F is 1, I remember it. If F is 0.5, it means I forget it somewhat, like I weaken my memory of it. Right? Likewise, the I is called the input gate. How much of the current input, Z is the current input, how much of the current input do I want to remember? Again, if I is 0, I don't remember it at all. if I is 1, I do remember the current input. You can see we add those together. So f and I dictate how much do I want to forget of the past, and I regulates how much of the current thing I'm looking at do I want to incorporate into my memory. Note these could both be 1, right? There's no necessary that they add to 1 or something like this. But these are called gates. And these gates made it possible to extend LSTMs without the problem of what we would usually call exploding gradients. The very basic LSTMs were implemented like something like this, like the hidden state at time step t plus 1 was sort of like the, you can you can choose, you can say, okay, it was like it was some sort of multiplication of the hidden state of t plus, so the w1 plus w2, the current input, right? So you might just say, well, I know neural networks, so I know like I just multiply by a weight, and then I may even push it through some sort of nonlinearity, right? But if we leave that away and just look at the basics, just want to incorporate the last state, and then I want to incorporate the current signal. The problem is, if you look at this, you do this over and over and over, right? You do this t plus 1 for t plus 2. You do the same again, but now your h is already the result of a previous multiplication. So as you go through time, you kind of multiply the same matrix over and over and over and over again, which leads to, if the spectral values of this matrix are larger than 1, you just get an explosion, because you essentially do the same multiplication with a number greater than 1 over and over and over and over again. If they are smaller than 1, very quickly you go to 0. So people had real problem getting gradients to flow through these time steps, because they would apply the same multiplication over and over. These gating functions, like additive updating of the hidden state using gating functions on the signals, mitigated that to a larger degree, especially the the exploding gradients is something that is not necessarily a problem here, because you're adding, you're not constantly multiplying, right? And you're only gating. You're not like here, you don't multiply all the time. All right, then there are some nonlinearities in here. So if you look at the LSTM formulation, you can see these gates, they are computed from the current input. They are also computed from the last hidden state, right? So you take, the gates are informed. The gates are not just fixed, the gates are informed. Like how much do I want to forget is informed by the current data and is informed by the last hidden state. Even the current input is modulated by the current data, obviously, like that's the main input here, but also by the last hidden state and so on. So, and then you can see these gates are computed. There is a sigmoid nonlinearity involved, which makes them between 0 and 1. This is tan h, I believe. So there's a couple of nonlinear, or this here is tan h, maybe? Yeah, it could be. And this here is just, I don't know. Here, they are the cell input activation functions, typically tan h. Okay. And then you can see here this error carousel as we just looked at it, and the hidden state is just produced. We call it, this is the output gate, right? The hidden state is also the output of the current time step. So every time step can give you an output value. You can use that for next token prediction. And that's achieved by shoving the C through a nonlinearity. So here you see that the dependence from C to the last C is de facto linear, right? It's if you think of how the gradient flows, there's no nonlinearity in the way it's linear. You can just zoom. Okay. And that, for example, is used in state space models. The fact that current time step to the next time step is linear, and how you aggregate data is fixed and is not data dependent, that fact is used to be able to scale it really efficiently. However, you look at the hidden state that is also passed from time step to time step, it's not the case. So the hidden state, has nonlinearities on it, is passed from time step to time step, and influences how the data is aggregated into the hidden state, or even the carousel. So this dependence of hidden state of the current step on the hidden state of the past step, that is a recurrent connection that has a nonlinearity inside of it, and that makes the whole thing not parallelizable. I need to wait for the last time step in the current layer before I can compute the next time step in the current layer. So if you compare this to transformers up here, if you're doing training, obviously if you're doing inference, you're doing next token prediction, yes, you need to wait for the previous thing to finish before you can start the next thing. But during training, where you have all the tokens available, you are able to just do all of this at the same time. You just, for all the tokens, not just for this one, but for all the tokens at the same time. And then you're able to do the next layer all at the same time, right? And that we call parallelizable training. It's among the things that make transformers really, really, really powerful. Because you can see, we have the time step dependence between, here we just have the time step dependence between the last layer's last step and the next layer's current step. In an LSTM, we also have connections like this and this right here. And these are the ones that then, especially if they're non-linear, these are the ones that make it really not train in a parallelizable fashion. So if I have 100 tokens in a sequence, training an LSTM on it is way slower than training a parallelizable transformer. Like with a transformer, I get 100 samples at the same time. In an LSTM, I do time step by time step, and I only get one sample at a time. All right. Okay, let's go to the two extensions that they do, the sLSTM and the mLSTM. Now the sLSTM, you can see right here, the first thing they say they do is we broadcast the original LSTM gating techniques. We broadcast the gating techniques. And if you look at, I think they say here, okay, they're now going to do this and that's not written here, but they're now going to do this in a vector fashion. So these gates here, are going to be vectors. The Z signal is going to be a vector, and therefore they're now going to use matrices here like W, 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 right? Big matrices, that gives you a vector. So the gates are vector. Then we have element-wise multiplication by the gates instead of scalar multiplication and so on. This, unless I'm super mistaken, has already been done for many, like 20 years or something like this. Like, it's very natural to do so, to say the hidden state is actually a vector and the gates are vectors. And however, doing this allows them to call this memory mixing. So you see, if you just apply this to scalars and you then do it twice, let's say you have two C's and two H's, right? So you have two scalars and you do all of this individually. It kind of means the current H only gets input from the last H of itself, right? Like, think I just have two of them, but the hidden connection, the recurrent connection are only between themselves, right? I only pass to my corresponding next time step H. And then if you H over there, right, you only pass to yours. However, if we have matrices right here, what matrices do, unless they are strictly diagonal, they take information from some dimensions and they can apply it to other dimensions, right? Every off-diagonal entry is essentially a information route between dimensions. So if I now consider all of these to be vectors, then that means that the dimension 1 of the hidden state can influence what's on dimension 4 of the forget gate on the next state. It's very natural properties of matrices, and you probably didn't even explicitly think of this, but by them starting at the scalar variant of LSTMs, now they're getting to call this memory mixing. So they say, oh, we have this new memory mixing thing, and they can have multiple memory cells, enable memory mixing via recurrent connections from hidden state, yada, yada, yada. Yeah, okay, so they call that memory mixing, like the thing that people are already doing. And then they go a step further and say, actually, instead of making this a full matrix, we can make this a block diagonal matrix, and then we have multi-head memory mixing, because now we only have memory mixing inside of these heads. Now that may very well be advantageous, right? Instead of fully memory mix everything, just restrict it to different, heads, might be really cool. But I feel they make the step here seem bigger than it is by touting this as like new memory mixing architecture. All right. The second thing they do is they replace the sigmoid nonlinearity, which was here and here, you'll remember, by an exponential function. And that is actually something new, right? The sigmoid nonlinearity is good, because if you don't want exploding gradients, then the sigmoid nonlinearity is pretty guaranteed to keep it between 0 and 1. However, it also is not so good, because it saturates very quickly. Like as soon as you go over here with your values, it's essentially a flat function. Your gradient is essentially 0. So it's good against gradient explosion, but not so good against vanishing gradients. And therefore they say, hey, what if we just take another nonlinearity that doesn't really saturate? And the exponential function is a good nonlinearity for that. Now, obviously, the exponential function has a few problems, namely it grows very quickly, and that's why they also, so you can see we have this new line right here, this new n line. This is a normalizer, and you can see that the h is now, h is now no longer computed as a nonlinear function of c, but h is now computed by dividing c by n. And then you can see what this n does is it simply accumulates f and I, because f and I now can be potentially quite big numbers, right? Keeping track of what they were in the past gives, so you sort of pull through, you aggregate the signal, but the signal is multiplied by large constants. So you also aggregate the constants themselves. By constants here, I don't mean constant, but like multipliers. You also aggregate them, and then each time step you simply divide one by the other in order to get a normalized output. As long as you can accumulate these things, you can sort of bring back from these giant numbers, you can kind of bring it back to a reasonable range by tracking that normalization state. So it's pretty cool, and it's an effective way of dealing with the exponential nonlinearity. And you'll notice conspicuously, we've also, as I said, dropped the nonlinearity here. They could still have one. They could still have a nonlinearity right there. They choose not to, so making the whole thing more linear. And also here, this probably will help preventing the kind of vanishing gradient thing. And since we already normalize, and they also do some gradient clipping, I recall, then we're probably fine. Lastly, they actually say, actually, we don't use the f and I you see above. We're actually using the f and I that you see right here by dividing. You know, this we're in kind of log space right here and subtract. So we're essentially dividing by this m term. The m term is like the max of this, and you can calculate this out. It actually doesn't change anything about the output. So the h value, the output value of each layer, and the gradients do not change. It's just kind of a numerical trick that they apply right here. So lots of numerics and tricks in order to mitigate the fact that they've just put in an exponential function instead of a sigmoid. Okay, so in summary, the sLSTM cell, what's actually new? There is a new nonlinearity right here. Then there is stuff you have to do to handle the fact that you just put in a new nonlinearity. They drop another nonlinearity, and they extend the memory mixing, even though I think that's a bit of an overstatement. So I'd rather say they introduce block diagonal matrices instead of full matrices in their recurrent computations. So by the way, also here, R, W, yeah. Good, that's one block. The other block, mLSTM. mLSTM relies on these associative memories. So the question is, I have at my disposal a matrix, D by D, okay? I need to store vectors of dimensionality D inside of the matrix. I can, so I want to store them and I want to retrieve them again. So each vector also comes with an equivalent key vector. So I want to store the vector somehow, like V, and then I want to use the key in order to retrieve it again. Now, one thing you could do is I can just put the first vector here and remember that particular key is at column 1. I can put the second one here. Remember that that particular key is at column 2, and so on. So you can see that works perfectly until capacity is full, and I am at, then no longer. And then I'm back into the exact same problem as with the LSTM. I'm like, well, which one do I need to override and by how much, right? So is there a better way? There is, or at least there could be. So what we can do, actually, instead of just randomly using the value and key, we can actually build an outer product of the value and the key. So that gives us a matrix. Now, that matrix is rank 1, but it kind of represents the value and the key, and then we can add that to the memory we already have. So the memory at the beginning is empty, but then gives us a matrix. Then we can have another value, V2, with key 2. We can make the outer product of those two and add those together. Oopsie, that's not a matrix. Matrices aren't circles. And we can do that infinitely long. Now, yes, the information will kind of override each other because we stack them on top, but what's actually happening here? So I have a memory 0, and I add to it V1, K1, outer product. Okay, that's my memory 1. Now, let's say this is empty at the beginning, so this is 0. What happens? How do I retrieve now? Well, I retrieve by multiplying my memory with the key, K1. Okay, what does that, if I just multiply this out, this is V1, K1 transposed, K1. Now, what we can do is we can, when we store stuff, just make the keys normalized. Like we just make them have length 1. In this case, this here just reduces to 1, right? This is a dot product, so it just reduces to the scalar 1, and I'm left with V1. Perfect recall. Let's say I take this M1 and I add another pair plus V2, K2. I get M2. Now, let's say again, so M2 is now has this and this inside of it. Let's say again, I want to retrieve key 1. So I multiply M2 by key 1. That gives me v1 k1t k1 plus v2 k2 transposed k1, right? Because this is this, and these here are the ones I stored. So what does that do? Well, this again goes to 1. And this here is the question. So there we make use of the fact that in high dimensions, if I have randomly distributed vectors, which we can make the keys be, maybe, sort of, let's just assume they are going to be approximately orthogonal. That's just the property of high dimensions, is just random vectors, they're orthogonal to each other. Like, unless they're really close, they don't have an inner product. So they're orthogonal, so they go to 0. So this is ish. So this falls away. This is ish v1 ish. So we were able to go with key 1 and again retrieve approximately v1. Now the question is obviously, yeah, with the way up here, we were also, like with stacking, we were also able to store 2 vectors, right? But if you read into the literature around this kind of memory under certain conditions and so on, you can see that this is a more optimal way of storing stuff. Like the distortion you get, the approximations you get of what you get out are quite good, even after you fill in more vectors than you technically have space for, right? You just keep adding rank 1 matrices on top of one another, and the memory capacity of that is quite large in comparison to other strategies. So this is essentially just a way to store stuff in, if you have a given amount of bits in memory. Okay, and yeah, arbitrarily much stuff in that. So this is what they do. So instead of updating a single vector with hidden state with a vector on top, they have a matrix memory. So the C is now capital, and they update it with this outer product. Obviously, if you go to the actual implementation, that's a bit more extended. So what we do is we no longer just build this Z value, which represents kind of the current state, but we now build the key and value. This is analogous, like the terminology here is analogous to transformer, but they're just things that are computed from the current inputs, and that we then store in the memory. At the same time, we also produce queries from the current memory, and then those queries get multiplied to the current memory, right? So this is now the retrieval step. So we've just added the current time step to the memory, and now we go and we retrieve from the memory. So we retrieve from the current time step, but also from the past. So we retrieve from this memory what interests us, and that's what the queries are for. Notice that this is all linear, so this can be highly parallelized. There is no nonlinear dependence on past steps and so on. Again, we pull in this normalizer because we have exponential nonlinearities, and you'll see here, rather than above we had dependence on h from the last step. We no longer have that. They're just like, these recurrent connections on the nonlinear hidden state. Let's just not do that. How bad can it be? So the only connection that goes from time step to time step is this C, and obviously the normalizer. They're all like additive and have no nonlinearities on the path here. There's a nonlinearity in F, but not on the, and the F only depends on the current time step. So this is notable, right? There is no past time that comes in here and sneaks through this nonlinearity and gets here and gets into the next hidden state, right? There's no nonlinearity on the path from one hidden state to the next hidden state. And that allows you to do this parallelizable training, because linear stuff is fast stuff. and is parallelizable stuff. So yeah, again, new nonlinearity, matrix memory instead of single vector memory. Then they reformulate stuff a bit so it looks more like transformers, even though you could probably formulate it in a way that looks a lot more similar to the stuff up here. And yeah, and that's that. I wonder if they just increase the dimensionality. Obviously now instead of d-dimensional memory, we have d by d dimensional memory. I wonder what happens if they just increase the hidden state, like by, square the dimension on that, and then like up project and do LSTM. Because, like ultimately you're just increasing the memory capacity here. And yes, you do it in this funky way, which is really cool. And like I'm on board with that. But I wonder what happens if you just do LSTM, you don't do hidden to hidden, like hidden nonlinear connections, and you just square the dimensions on the hidden state. But notably, there is no parameters involved in this. So this is pretty cool. So there's parameters here in building like queries, keys, and values, but there's no parameters necessarily in the kind of storing and retrieval procedure as such. So I guess if you had to up project to huge dimension, you would also have to have huge amounts of parameters. So maybe, I don't know. Maybe that's the answer. All right. Then they wonder, how do we make this into blocks? So now we have, now we have blocks, right? These things are blocks. Now, how do we make them into, blocks. Yeah, how do we make blocks from, so here we have like an sLSTM, and here we have like an mLSTM, and we wonder, how do we embed them into, because transformers, they don't just have attention, they have like attention and residual connections and normalization and up projection, right? The feed forward layers and so on. Okay, their answer is going to be for the sLSTM. They found it to be beneficial to just do that sLSTM stuff here, and then do this up here is essentially a what would be the feed forward network in a transformer. And then here, sorry, in the mLSTM, they do the up projection of the feed forward network here. Then they do all of that stuff in the higher dimension, and then they do the down projection after that. So they kind of up project and then after that down project. So yeah, they must have found that this is more advantageous. If you actually look at it, like we can quickly look at that, they have in the appendix, they have these actual drawings. All right, the appendix is fairly extensive, which is good. Okay, so you see here, there's more to it. So you see there's incoming signal, there's layer norm, and then the input and forget gate computation. For some reason, just go to like a conv of window size 4 convolutional layer, followed by like a nonlinearity, and then go into this block diagonal multi-head memory mixing thing. And you can see this here symbolizes recurrent connection. Whereas the Z and O, like the output gate and the representation of the current input, they don't go through that. Okay, then we have a group norm, and we have an up projection, and then there is like a another nonlinearity in here, and then you have a down projection again. So again, this is a bit akin to the feed forward network in a transformer block, and you have a residual connection all around that. Whereas the mLSTM block, you see first the up projection, then again, part of your, like the queries and keys here go through this conv and swish. This might be to substitute the missing softmax, right? Because the softmax would exactly act on the queries and keys. But yeah, the values don't go through that. Then there's a layer skip. So this is another residual connection that's just introduced on top of this residual connection right here. And then I guess this here-ish is then akin to the feed forward layer of the transformer. They more talk about pre-up project and post-up project in this stuff. I guess they just tried around a little bit and they found that this works better. Okay, obviously, if you up project first, then your matrix memory in here needs to be even bigger. And that's what they tout as one of the main limitations right here, is that yes, we don't do the transformer memory thing. We have constant memory. However, that constant memory can be large. So they have a linear computation and constant memory complexity with respect to the sequence length. Since it's compressive, it's well suited for yada yada. Memory of the mLSTM does not require parameters, but is computationally expensive through its D by D matrix memory and D by D update. Hello, this is Yannick from the future. Unfortunately, my screen recording OBS has crashed. Well, it was my mistake because my laptop ran out of battery, and then I was interrupted, and then when I came back, everything was crashed. So I lost the second half of this video, but it was actually to the good, because I had the opportunity to have a conversation with the authors since. So that was really cool. The next part that would come here are experimental evaluations. Now, the experimental evaluations are really thorough. They do post a lot of numbers on a lot of different tasks and so on. And what it looks like is that it's not like a super clear winner, but that's not what they aim for. But rather, it is up there, as you would say. It is for some tasks, especially the tasks where recurrent neural networks like recurrency helps. It's really good at, obviously. And for sort of general language modeling and general LLM evaluations, you can say it is competitive with similar models. Now, whether it's better, worse, a bit better, and whatnot, I think that is left up to the exact evaluation and exact benchmark. There has been a bit of criticism in how they implemented the baselines and compared to the baselines. For example, the process is obviously not very up to introspection. It seems like there might have been some, not as much effort into the baselines as there was into their models, which it's still a research paper. And yes, that's how everybody does things. However, through the conversations with the authors, which again, very lucky that I was able to have that, they've told me that they would update the paper soon with updated numbers on the baselines. As far as I understand, they have trained some of the baselines only in 16-bit precision, where it would be important to use mixed precision. And that's what they managed to do now. And so they will update the paper with that. So I'm going to leave out any sort of comments on the evaluations as such. Just the global picture is that it is in there in the current models. Like, what you can say is that if you compare xLSTM to Llama, Mamba, whatnot models, then at least they're going to perform similarly. And yeah, time will tell if people actually adopt this. Time will tell if this is actually useful in real world setting. Time will tell if what they say right here, you can train it really well, whether that's really the case. I think that just requires a lot of different people to either incorporate this or incorporate parts of it into their deployments. They do have a section on limitations, which is also very cool. So, and just jumped away from that. And they also have a section on conclusion. So in the limitations, they do mention, hey, look, we cannot do a fast parallel implementation of training. That's kind of out of the scope. I cannot. Can I do this? No, I can't. Oh well. They cannot do fast parallel training because there is a recurrency involved. Nevertheless, they developed the fast CUDA kernel for that. Also, if depending on how big you make your mLSTM memory, obviously, that alone is a lot of numbers that require some crunching, even if it's not recurrent. Number crunching is expensive, and therefore the extra size of that memory introduces extra constant cost, if you will, constant factor cost. And then, yeah, lastly, they say due to the expensive computational load for large language experiments, we did neither fully optimize the architecture nor the hyperparameters, especially for a larger xLSTM architecture. In the conclusion, they say their original question being, how far do we get in language modeling when scaling LSTM to billions of parameters? So far, we can answer at least as far as current technologies like transformers or state space models. Again, whether that's 100% accurate, I think time will tell. What we can say, at least from this paper, is it's in there somewhere. They also say they would release code and maybe also models, so people might be able to check for themselves once that's out. Yeah, so this was it. Sorry that the second half here went bust, but I hope you were able to make sense out of a bit of this, and I wish you a wonderful rest of the day. By the way, if you're interested in paper discussions, we do paper discussions almost every Saturday on Discord. In fact, on our Discord, there are people doing paper discussions almost every day, self-organized, very, very cool, very, very big effort of the people involved. And yeah, if you're interested, come join. And that's it. Bye-bye.